Okay, thanks. Well, as Brent said, I'm an assistant professor at McGill University of Civil Engineering, and my research interests are very much focused on investigating these associations between transportation and air quality. And I do have a few different research streams that I'm pursuing with my graduate students, and they're all related. They're all focused on that kind of association. And we do this at three different scales, three different levels through development of regional level models that can assist in long range visioning exercises at the neighborhood design level. And I'm going to talk about an air pollution monitoring campaign, near road monitoring campaign that we conducted in Montreal, which was mostly focused on cyclists, but it's also monitoring near road air quality. And the last study that I'll talk about is individual behavior, so we're doing personal exposure measurements and linking that with health effects, and that was collaboration with epidemiologists. Now, I'm sure you all understand the many motivations for doing research in traffic-related air pollution. In urban areas, transportation is still the dominant source of air pollution. Now, of course, internal combustion engine has made tremendous progress. Vehicle emission factors are lower nowadays. Air pollution still remains a problem because of the spatial distribution of people, jobs, and activities. More and more we perform activities, we live closer to busier roads, and with urban planning agendas that are focusing on denser, mixed-use urban environments that promote walking and cycling. Not that I'm saying that this is not something good, this is excellent, but what we're doing is we're bringing people even closer to the sources of air pollution without doing much to reducing the emissions per se. So that's why I think air pollution is still a very important problem in urban areas, even in Canadian cities, where sometimes we struggle with detecting air pollutants. That doesn't mean that we are safe. Now, traveling, commuting contributes an important part of a person's exposure, being on the bus, being in the car, walking or cycling. And I do a lot of that kind of research. Now, early literature used to always say that people who are in their cars are exposed to the highest level of pollutions because you're in vehicle, it accumulates. But that was only because they were looking at concentrations in vehicles. The new body of literature says that there is no doubt that cyclists are the ones who are exposed to the highest level of air pollution because if you factor in the breathing rate, the dosage, they are incurring the highest dosage. There's still a lot of literature looking at air pollution during commuting. Now, a little bit on the health effects. Uh, the literature really swells with studies that have linked traffic-related air pollution with physiological effects, with health effects. Now, the issues that the health effects that are known, that are not on the slides, are everything that is respiratory. Incidence of asthma and aggravation of asthma. And a lot of researchers in epidemiology would tell you that these are causal associations. We already know that traffic-related air pollution does aggravate asthma or even causes asthma. Now, the other new effects that have been now being that we see in the literature are two things: cardiovascular. So there's a lot of research on cardiovascular mortality, development of cardiovascular diseases as a result of exposure to traffic-related air pollution. I've actually selected here mostly Canadian studies, and I have two studies here that I'm talking about because I'll refer to them later. These were by Montreal groups at McGill and Université de Montréal that had linked the exposure to traffic related to NO2, which is considered as as a marker of traffic pollution, with the incidence of breast cancer and the prostate cancer. So very briefly, I already mentioned that. I'm going to talk about three different studies. One is the development of a regional transport and emission model. Another one is a campaign to do near road monitoring and trying to investigate the effects, the predictors of levels around near road. And the third one is a personal level measurement. And while going through that, I'm going to talk about two different levels. Well, how we investigated this association, the research, but also the knowledge dissemination, the knowledge translation. How does each scale of analysis translate into informing public policy and informing the public at large? And how can we develop tools that can assist people in making better decisions? So I'll jump to the regional model for Montreal. So this was done for the Montreal metropolitan area. And for those of you who may or may not be familiar with Montreal, Montreal has the main island, which is considered nowadays the city of Montreal. But then it also have the island of Laval, the South Shore, Longueuil, and then going up to the Laurentians. So this is a fairly large area, which is considered the MMR. Apart from the central core within the city of Montreal, everything else is very suburban, so very sprawled development. And what we did at this stage, and there's definitely much better models on the transportation side here in Toronto that Eric is developing with activity-based models, but we still wanted to develop a framework that would capture individual level emissions. So we have here two, and I don't need you to go through to be able to read, that's fine. I'm just going to explain very briefly the two main pillars. The first pillar was a regional traffic assignment model that we've developed in Vizu. And from that traffic assignment, what we did was to extract the path. So we're extracting, all the different paths between every origin and every destination. And then what we did with these paths is we associated them on the network, just very randomly, just using the amount of traffic on every path, and with some rule-based model, making sure that we're not allocating every person on the same path. And the reason why we did that is because we want to be able to track individuals, to track all the different segments that they are going through from an origin to a destination. Now, we also purchased the database for vehicle ownership from the Société de l'Assurance Automobile du Québec, so it's a motor vehicle registry, which gives us at the level of the the FSA level, so the three letters of the postal code, all the vehicles that are owned by households. And then that allows you to kind of associate a vehicle to a certain trip, to a certain household, based on different constraints that we know from the OD survey about the vehicle ownership. Then we use the model MOVES, which is a model that developed by the US EPA. We fitted it obviously with input data reflecting Montreal. And we are also have a student that is calibrating MOVES. So we are collecting GPS data, drive cycles for buses, for cars, and changing the operational mode distributions within that model to reflect the Montreal conditions. It's actually, once you get into it and understand it, it's not that hard to be able to calibrate these up mode distributions, but you just have to have good data. Now, all of these pieces go into what we call the vehicle allocation slash emission post-processor. So we're allocating a vehicle to a certain trip. We're looking at the links between all the different trips. Because there's so much randomness in the model, we actually run it many times, so we don't generate one deterministic outcome. And you'll see that in the results. And what we are able to generate are two things: the running emissions, so the emissions that are occurring on the road network, and the start emissions, which are the emissions that occur as soon as you turn off your engine because the engine is not yet at an optimal temperature. And these start emissions depend on how long your vehicle was off before it was turned on, so the soak time. And because we have that information from the OD survey, we know the time at which each trip had occurred. We can calculate how much time the vehicle was off before it was actually turned on. So just very briefly to give you an idea, different pieces of that methodology. This is the structure of the vehicle ownership database that we have obtained. So for every FSA, we have the types of vehicles, the age distribution, and basically we have the different types of cars that are covered in the database. And we are generating these distributions at an FSA level. The light blue here that you see are passenger cars between 1 ton and 1.5 tons. That's why they are the most common. And then we are allocating very randomly a vehicle from this distribution into a certain trip and making it consistent over the entire route for every individual. Now, we did a lot of work in looking at the sensitivity of the model to selected input distributions. Input distributions or different types of inputs as well. This gives you an idea of what you get if you're including the vehicle starts or if you are ignoring the vehicle starts. So that really tells you it's very important to include the emissions that are occurring as soon as you start your vehicle. They are a significant component. Now, this is for total hydrocarbons, and so that's why it's important. If we're doing other pollutants, you wouldn't actually see that big difference. It's also important to account for the seasonality, and MOVES does allow for different levels of meteorological inputs to be fed in. You can put an aggregate input, but you can actually detail it. And then you can see the differences between summer conditions and winter conditions. This shows you the sensitivity of emissions to the soak time. These are the start emissions. So basically, up to a soak time of about 200 minutes. So about 2 to 3 hours, you really are influencing the start emissions very much. Then after that, if the vehicle was turned off overnight or over the span of 3 to 4 days, it doesn't make that big of a difference at that stage. Now, what you see here are the daily regional emissions, assuming two different levels of aggregation in the inputs. What we assumed first is, well, what if we didn't know the distribution of cars and we thought that everybody's driving a passenger car, and these are the emissions basically that you will get. Well, let's assume, let's take the actual distribution of vehicles, and this is where you get. So you see a very big difference as well. Looking at the age distribution, so the very dark line is the actual age distribution of the vehicle fleet that we have. And the light gray is assuming that every vehicle is an average car and assuming that it's 8 years old, which is the average age of the vehicle in Montreal. And you're actually, not doing well either. You will see very, very tiny error bars. You may or may not see them. That's based on the many different simulations that we're doing, and that's the effect of the randomness in the model, which compared to the size of the other inputs is not that large. But maybe that's also an artifact of how we've built that model. And we've also run a sensitivity to, assuming that we're looking at the link speed or at the trip speed or at the network level speed. And I'm not going to go into details in this, but that gives you, the path, the tree of how we're just, making one input, very, very aggregate, and another input looking at the distribution, and where you can be, how you can be really doing at a finer resolution, or if you're not doing a finer resolution. And we're trying to understand how these errors can sometimes cancel each other, and you get lucky and you don't think that you've made any errors, or sometimes they would actually, propagate. Now, this is the first piece of result. Because we're doing this analysis on a person level, this is actually aggregated to the TAZ, but just for visual purposes. We might as well we could be plotting that for individuals because we're calculating it at an individual level. This is NOx emissions that are generated per person, but then we bring them back to the zone of where they live, to the household location. The dark areas are the ones where we have high emissions per person. The light areas are the ones where you have low emissions per person. This is the island of Montreal, and these are the gray, these are the West Islands, so your typical suburban development. What basically this map tells you is that everyone who does not live in the central core of Montreal emits a very high level of total NOxes based on the trips that they conduct in their household. And everyone who is living within the central city is actually emitting a very low level. That's very intuitive. I mean, you don't need that kind of model to really tell you that people who live in the suburb are generating emissions. But then the interesting part is to be able to capture that and quantify that. Now, if I overlay the emissions that are occurring on the road network over this map, just even visually, qualitatively, you're going to be able to see that while most of these emissions are occurring in the light gray areas, where people who are not emitting themselves are actually exposed to really high levels of pollution. And so if I do the opposite map, if I plot the NOx emissions that are occurring in traffic analysis zones, I get the opposite. I get that the central areas are in the very dark gray, so these are individuals who are exposed to high levels of emissions, and all the suburbs and the areas around that in the light gray, these are the individuals that are not exposed to high level of emissions. At this stage, there are no dispersion results because we're still working on the dispersion model, so this is just a measure of the emission density, where it's occurring and where it's coming from. Now, so what we did was we went at the individual level, and we compiled the data for the vehicle ownership, the type of vehicles that are owned at the individual level, and characteristics of the land use. And we did a regression of what makes you an emitter and what makes you a person that is exposed to emissions. These are factors, not variables. And so basically, if you are living in a dense, walkable, transit-oriented zone, that makes you less of an emitter and more of a person that is exposed to air pollution. If you are somebody who have a high car ownership and large vehicles, that also makes you more an emitter and less of a person exposed. But if you are high income with newer vehicles, that makes you less of an emitter and more of a person exposed. And we try to, dive into these things, and you probably have guessed it. It's very intuitive, and the data shows us this is the difference between the rich of the inner city and the rich of the suburbs. So they're both are high-income households. They both have a lot new vehicles, but one type of household has more vehicle and bigger vehicle. The other type has still newer vehicles, but then not as many, and they probably don't do trips that are this long. Now this shows you a cluster analysis of looking at this difference between emissions generated and exposed to. And I don't need you to look at the details in the legend. You only have to focus at the very dark areas and the very light areas. The very dark areas are the individuals who emit a lot and are exposed to very little of what they emit. And the light areas are those people who emit very little and are exposed to a lot. And that's, getting into that issue of equity. Who are the emitters? Who are the people who are exposed? And the pollution that you're breathing is coming from whom and who is generated that? This was for air pollutants. We did that the same thing for greenhouse gases, and the greenhouse gas map actually looks even more sharp, more striking, because it's just greenhouse gases, and then they really are a function of the trip distance and the frequency of trips. And the last piece of result that I want to share with you here is something we call the triple burden. So that's a map that illustrates social disadvantage, that we've calculated the social disadvantage index at the individual level, which is an index that is based on the household income, the proportion of immigrants, the level of education, etc. So social disadvantage, high exposure to traffic-related air pollution, and small proportion of emissions generated. And the people who are in the dark, the very dark, are those who are incurring that triple burden. So very high social disadvantage, very high exposure to NOx emissions, and very low generation of NOx emissions. And that's very important for public policy to be able to identify those pockets of and those kind of neighborhoods. I'm not going to go through this. The only reason why I put this, and this is not a slide of mine, this is from Louis Rouen, who is the director of the Département de Santé Publique, so the Montreal Department of Public Health, because Public Health Montreal is actually funding this work. It's not the Ministry of Transportation, it's not the City of Montreal, it's the Public Health Department. And that's very, very interesting, because they get this association with transportation, air pollution. They are very interested in having that capability in-house and be able to evaluate long-range visioning exercises. Their plan, whether or not it is really feasible, is to do this kind of analysis, calculate air pollution through a dispersion model, and then link that with risks of respiratory, cardiovascular disease, traffic injuries, or calculate accidents, and all based on risk functions, as well as looking at physical activity from walking and cycling. I do always caution that these kinds of models are not meant to look at the individual level, but they give you an idea of the broad trends. Now, another application that we're doing is, so we took this model, and we took that breast cancer study, the postmenopausal breast cancer study, which was used using a land use regression model for NO2 for Montreal, and where there has been an association between exposure to NO2 and the odds of breast cancer. And we asked the questions, well, can a transport model actually predict the risk of breast cancer just as well as a land use regression model? Because the LURs are expensive. You have to have fixed monitors, and really their accuracy is as good as the spatial extent of your monitors. And so we took this breast cancer cohort, and we actually associated. We looked at the effects from the models. What we see is that we do get very similar ORs, but they are toned down. They're actually lower than what you get with the NO2. However, the confidence interval of our ORs is narrower, and we are within the same confidence interval of the previous breast cancer study. And there we're fighting with the epidemiologists who developed that study. They say, well, that means that you have misclassification in the data. And we say, well, if our confidence interval band is within yours, then how can you say that we are getting any different results? This is still a study in progress, so we don't have conclusive results. but we're actually validating this model with the LUR to kind of see where we're doing well, how are we agreeing, and where do we not agree. I'm not going to bother explaining this now, but if you have questions, we can talk about it. Now, this is where I want to stop with respect to the regional modeling capability. And the next study that I want to talk about is a study where we investigated the determinants of traffic emissions and near-road air pollution. And the first angle that I want to talk about is one of exposure monitoring. I call it exposure monitoring. We really are not interested in what people are exposed to, but we're interested in looking at near-road air quality levels. So this was a data collection campaign that we did in the summer of 2012. And what I did is hired a lot of students who are cyclists, and we fitted their bicycles, well, our bicycles actually, with air pollution monitoring equipment. And I'll show you the pictures. And we had tubing running on the frame of the bikes. They had GPS devices. They had GoPro cameras to just look at environmental attributes. And their job was to actually cycle around Montreal for an entire summer and collect data. Now, that's a dream job for an undergraduate student to do this all summer, but it actually gets really tiring because every day they have to check in, they have to calibrate their equipment, they have to synchronize their clock, they have to load their bike, and they actually cycle 70 kilometers every day because we need a lot of routes. And they come back, and then they have to match all of the XY coordinates with the air pollution data, do some quality control, load the data. So it gets really tiring. And the way we do it is sometimes we have, 1 week of data collection and 1 week where they spend it in the lab and they rest a little bit. And it kind of wears out at the end of the summer. They get really tired. Where's Graham? Is Graham here? Yeah, Graham did that for a summer. So this is to show you the extent of the data that we have collected on the island. So we've collected data for 475 kilometers of unique roadways. We also collected data for 350 kilometers of cycling facilities. This was kind of also tagged on a cyclist exposure to air pollution study. But I mean, you can think about it either way. We are measuring near road air pollution. And we selected routes, to reflect the diversity of microenvironments. We had 15 routes that started at McGill. We had 10 routes that started at peripheral regions, so they have to load the bikes on a van and drive and do the suburban routes. It wasn't feasible to start it at McGill. So we had in total 25 routes, but the concept of a route means nothing. The routes are just, a certain amount of time that they're going to spend on the road network. And then every route, they're obviously repeating it in the morning peak period, afternoon peak period. We have repeated measures over the sampling campaign. This is Graham again on his project bicycle. So it's it's very simple setup. It's we have in one of the upper picture we have a condensation particle counter for ultrafine particles and a microethylometer for black carbon. And you have the tubing running on the frame of the bike. We have the camera as well as the GPS. And so the other data sources that we collected other than air quality is the land use data. So you have the land use characteristics on every single roadway. So they did a lot of Google Street View data collection on Google Street View, as well as some validations in the field. The extent of the network is so big, it's very hard to just sit on every road segment and measure these things. And what we wanted to do is try to see whether, GIS readily available predictors would actually do a good job in that kind of mobile monitoring campaign. We also used the traffic volumes from the regional model because in such a very large campaign, you can't sit on the side of the road and count cars. It's impossible. And we were interested to see how well they would do. Not very well, with respect as predictors. But the problem is that with these kind of models, you only have one type of vehicles, which are cars. And it's actually the vehicle mix that really influences near road levels, the truck ratio, the ratio of SUVs. We saw that as an important predictor. And then we conducted some statistical analysis. Now, the first part of data processing is that you have all those GPS points. And remember, every segment can be cycled up to 100 times because some segments are common among many routes and they are repeated many times. And so you have all those GPS traces that you have to match onto the segment. Now, that's not a guessing exercise because we know where they should be. We've developed the routes, we've identified them. So the algorithm is much easier because once you see any XY coordinate, any point, you know what time it was done, what day it was done, and who's the team who's doing it. So it's not very hard to really actually to match it on the segment they should be on. And this shows you a map of the distribution of ultrafine particles in Montreal. And this is in quintiles. The darker ones, the black ones, are UFP levels ranging from 28,000 to 75,000 particles, which is relatively high. I mean, the average, in an urban area would be around 20,000. That's what you would encounter. So I would say anything in the red and in the black is relatively elevated UFPs. And this is an average over that entire campaign. We obviously did see peaks that were higher than that. We can't say much more about UFPs because there's no standard for ultrafine particles, so we don't know what level is safe. This shows you the distribution of black carbon. Again, very similar spatial distributions. All these routes that are, especially on the North Shore, had low levels. In the West Island, sometimes yes, sometimes not really, because you have really big highways. Actually, one thing that I want to note here is, I don't know how many of you are familiar with Montreal. This is a route on the Lachine Canal. This is considered the most scenic route. Everyone who's a tourist who goes to Montreal wants to bike on the Lachine Canal. It was actually the most polluted. It is the most polluted bike path in Montreal because of its proximity. It's very close to Highway 20, Highway 15, so it gets a lot of these emissions. So this shows you the regression of ultrafine particles. And I just selected a few variables, and we can talk about this after. Wind speed, temperature are effects that we expect to observe. We've seen that in all other studies. They have a negative coefficient, especially for ultrafine particles. Nice thing is distance from a restaurant seemed to be significant with a negative effect, and it was able to coexist with other variables. And it turns out that actually restaurants, especially fast food, smoke, does include a lot of UFPs, and it's no surprise because if you cook at home, also in indoor air quality, and UFPs are very high in indoor environments. The other thing is the building footprint that was interesting. So we looked at the closeness of the buildings and the amount of buildings around the roadway to kind of get a measure of the urban canyon effect. And we do see that building footprint does have a significant impact on air pollution. Now, the interesting part of the survey, and I'm just going to pause here a little bit because this is mobile monitoring. And normally, you have fixed site measurement, you get an integrated measure, you have a fixed measurement for about 2 weeks, you're getting a good average, a 2-week average. And what we wanted to see was that in a mobile campaign where the spatial variability is unparalleled, there is no way you can cover as much with fixed monitors and what we do when we are on bike. But the temporal resolution, I mean, how long are you on a segment? You're 20 seconds, 30 seconds on a segment. Even if you do it 20 or 30 times over the sampling campaign, that's really a very short-term average that we're capturing. And we were interested to see, well, what is the potential of this kind of mobile monitoring in the development of land use regression models? And that's, I mean, it's still, I'm not really sure, because it allows you to have, refined variables to look at what's happening near the roadways. But you're not getting models with very high R-squares like you would get in, not that it's a problem, but you're not getting these models that are excellent maybe for prediction purposes. Now, in another campaign, we actually did fixed measurements on the two sides of the road to look at the difference between levels on both sides of the road. And we explored the effects of road width, wind speed, wind orthogonality, so calculated the angle between the wind and the roadway. We took the sine of the angle, and we saw that, as the angle is more orthogonal to the roadway, the difference between the two sides of the road are higher. We looked at the effect of buildings on both sides, and we did some other measures of the aspect ratio of the urban canyon, the height of the building versus the width of the buildings, and we did see effects on, increasing the differential between both sides of the road, which may or may have significant health effects. What it basically tells you is that depending on the side of the road you're walking on, you can be exposed to very different concentrations. And we know that by theory, it's nice to be able to capture that. I do say that these are all small effects. They are significant. You don't get incredibly long routes that go through all the different parks in in the city. And that's an example of how this is now on a web page. It's actually it's available. We have a comment box so people can send comments if we are coming up with totally ridiculous routes. They could let us know, and we can improve that. I'm not saying that this should be used as an exposure management device or a route planner. It allows people to explore what is there. Again, the actual specific route you may or may not be really right, and cyclists. I mean, there's many factors that influence cyclists' route selection. We're not getting into that. What we did is we wanted to look at the potential benefits of this tool in reducing cyclist exposure. So we took data from about 2,000 cycling trips. We extracted them from the 2008 OD survey. We ran them through the algorithm, and we looked at the lowest exposure versus the shortest path. And we saw that there was actually, in 50% of the trips, there was a lowest exposure route available. So the other trips, the shortest path is actually your lowest exposure. So you can do better than that. And then for those 50% of the trip, we did see a decrease in cumulative exposure of about 40% in average. You can say this is important, this may not be important. But for somebody who's doing this every single day over the span of years, this might be important. The interesting thing is that we see that the benefits of decreased exposure can be achieved with just cycling maybe sometimes less than 1 kilometer to achieve that reduced exposure. So you're not really going out of your way to reduce your exposure. You could actually achieve that by biking a few hundred meters more. I will stop here, but then tied with that, I want to talk about, it's not near road air pollution, but traffic emissions, and looking at an example of simulating emissions at a microscopic scale. And that really will allow us to understand the associations between traffic emissions and near road air pollution. The example that I want to give you, and in the interest of time, I'm not going to do it in details, but we can talk about it, is on transit emissions. I've actually been doing a lot of work on bus emissions because it's much easier to collect data on buses. I mean, you can get the GPS data, you can actually ride the bus instead of giving GPS devices to passengers. This is a corridor called the Côte des Neiges corridor. It's very busy. It's one of the busiest corridors in Montreal. It runs from the downtown all the way to Ville de Mont-Royal, TMR. It really has very high ridership. And what we did is that, well, we obviously rode the bus many times. We took the data from STM, the GPS location data, but we rode the bus. We did install GPS devices, and the students were counting the number of passengers boarding, alighting. They were counting the amount of dwell time. They're also estimating the amount of dwell times when the doors are closed, but the bus is actually also dwelling. And we did simulate the emissions. This is using moves, but this is actually, we did that outside of moves. We actually calculated the vehicle specific power, the VSPs, ran the op-mode distribution, and just used moves as kind of a macro to calculate these things. Now what we did is we've investigated a few parameters that affect bus emissions. Speed is something we all understand. You can have, at different average speeds, you're going to have different emissions for the bus. This is not an average speed model. This is average speed based on different traffic loadings and different congestion conditions. But we also looked at the effect of grade, ranging from minus 7.5% to plus 0.75%. And I have to say, in Montreal, we actually have grades that are even steeper than that. And you could clearly see the effect of grade on emissions. You can also see kind of the effect of grade and speed, that as the speed becomes lower, the grade effect becomes even more important. And these box plots do illustrate that we've done many different runs on this. This is not just a single bus. The other thing that we looked at is the effect of passenger load on transit emissions, because everybody knows that every additional passenger on the bus is increasing the weight of the bus, so it's going to increase the emissions. But the total emissions of the bus are being divided by the total number of passengers on the bus. So what is the marginal effect of every individual person on the bus? So if you look at the red line, this is the emission rate in gram per mile for the bus from a load factor of 0.2, so one passenger, all the way to 2, which is 76 passengers for a standard bus. So clearly, you have more people on the bus, you have more load, so you're going to get increased emissions. Now the blue line shows you the per passenger emissions, and this is the scale on the right. So every additional passenger on the bus, you're dividing by a higher number and you're increasing. But what you see here is that by about the time the bus is full, every additional passenger, and we see this in the numbers, maybe it's not very clear in the graph, every additional passenger no longer offsets their weight on the bus. And that's kind of to tell you that you don't need to overload your buses to achieve lower per passenger emissions. By the time the bus is full, you are actually achieving that benefit. I'll stop at that in the interest of time, and I'm going to move on to talk about the last study, which is on personal exposure monitoring and actually measuring the health effects. This was done in collaboration with a Health Canada epidemiologist and a McGill epidemiologist. And what we did here, this was a women's study only. We actually decided to focus only on women. We recruited 50 female cyclists. And what we did is that we had them cycle on a high traffic route, on a low traffic route, and we knew the levels of pollution, so they were really high, really low, and indoor cycling for control. And we structured a study whereby, again, it might sound interesting when you're a female cyclist, it can end up being tiring at the end of the day. You check in at the beginning of the day, we take your baseline resting heart rate, we install a Holter monitor on you for the entire day. You do 2 hours of cycling, you come back, and then we measure, so we trigger the Holter monitor and we measure certain parameters that I'll talk about right after cycling, 1 hour after cycling, 2 hours after cycling, and then 3 hours after cycling, and then we do a checkout interview. And what we were trying to see here was that whether we could measure significant association between exposure to air pollution and cardiovascular outcomes. And the two cardiovascular outcomes we were looking at, we were measuring is, one of them is endothelial function. Endothelial function is actually related to oxidative stress, and that's what my collaborator has explained to me. We measure that through, you basically have two probes on your two fingers, and you have one arm that gets occluded. So for 5 minutes, we actually have this cuff that occludes the blood flow in your arm. It is very tiring, and so this is why we didn't want to do it too many times during the day. And then after those 5 minutes, we release the cuff, and then we measure the blood flow on that arm versus the other arm. And that ratio, which is called the RHI, gives us an idea of the difference. There is evidence in the literature that certain air pollutants do have an effect on oxidative stress and on the ability of your blood to actually flow faster or slower. The other measure is heart rate variability. And very late term, heart rate variability really captures how well your heart rate responds to different levels of physical activity. So if you're sitting, your heart rate is lower, and suddenly you stand up, your heart rate starts racing. There is also evidence from the literature that exposure to air pollution does mess up that basically your heart rate is no longer catching up to those very fast changes in activity. And there are also different variables that explain heart rate variability. We did not analyze the cards from the Holter monitors ourselves. We did not have the capability to do that. So these were analyzed from the University of Ottawa Cardiac Institute. So jumping into a little bit of the results. So looking at blood pressure and looking at microvascular function. So the RHI is what I explained, the indicator of endothelial function. What we did see is with ultrafine particles, the effect that we observed. With UFPs, we did see a decrease in endothelial function of about 5%. And the effect on blood pressure, what we saw was with ozone. We did see an effect on increasing heart pressure, the systolic and the diastolic, both of them in ozone. And these decreases are related with an increase in the interquartile range for those air pollutants. Now, this is just to show you again, all of these results, you have to take them also very critically. This is the change, the percent change in RHI, so the endothelial function, as a function of UFP concentration. You actually, I'm sorry, you don't see the confidence interval. It would have been very important to see the confidence interval. But it is in a very light gray. It is a significant effect. It is mild, nonetheless. And here I did make a summary of the observed effects. What we see is that the short-term exposure to UFPs during physical activity was associated with decreased endothelial function 3 hours of exposure. Ozone was associated with increased blood pressure 3 hours after exposure, and we did see effects also from PM 2.5 and NO2. The most important thing is that the effects are small in magnitude, but they may be relevant for sensitive populations. The other thing to say is that, again, I'm also very critical of the conclusion of identifying certain pollutants with the effect, because people are just, you're breathing the soup of pollutants, and there are pollutants that we're not measuring that could be causing the effect, but we just didn't measure them. And this gives me about 5 minutes to talk about conclusions and some future research. Now, I've talked about modeling at different scales, the regional scale, which allows us to look at spatial patterns, spatial distribution, evaluate the effects of long-range visioning exercises without really very much fidelity at the individual level. I caution against using them at the individual level. They're not meant to allow you to derive exposure unless you have an actual cohort and you know who these individuals are. The other level of analysis would be the near road monitoring, and then the future step would be to try to actually associate these very refined levels of traffic emissions with air pollution levels on the road and see how well these associations are and how well we are able to predict near road air pollution with respect to what we measure. The third one is personal exposure monitoring. I'm not sure, I don't know how much more personal exposure monitoring I'll be doing in the near term. I mean, these are really interesting studies, but they're very, very, very expensive. And again, 50 females is not a very big sample size. You probably need more than that, and you probably need a lot more funding. So the few research questions that I do want to engage in moving on. This is actually a SHRP grant that I'm hoping to put together by the LOIs next week. The question here would be, can we develop exposure surfaces for urban areas that reflect the expected impact of air pollution mixtures on physiological parameters relevant to cardiovascular health? So instead of having one surface for every different pollutant, you actually have a multi-pollutant surface that shows you a biological outcome, a health outcome, rather than just a level of concentration of air pollution. And then through simulation, can we identify practical interventions related to traffic and the built environment that could decrease the health impact within pockets that we could identify as problem areas? But that really needs a lot of air pollution measurements, a lot of modeling, and then you need cohorts. You need a number of cohorts to be able to test that information. Now, with respect to refining traffic emissions model, and this is definitely would be my CFI would be to purchase what we call PEMS, a portable emissions modeling monitoring system. And these are systems that you could install and measure emissions for cars in real world. There's obviously a lot of dynamometer testing that are done in labs that are excellent, that give you a much better profile for the chemicals that are generated by cars. But if you want to do that in real world driving conditions, and even though I have cars in this picture, I'll probably start that with transit buses because we have a lot more momentum in transit emissions. And the two questions that I would want to answer is, or explore, would be, well, how do those base emission rates that you're testing in the lab from dynamometer tests vary under real-world conditions? The other question that is of a lot of interest to me is, what is the level of speed aggregation that is acceptable for emissions modeling? Everyone says the gold standard is a second by second, but it's impossible. You can't simulate an urban area, and even models like VISM or Paramix, we still don't trust that they are giving you acceleration and deceleration rates that are realistic. So, well, what is possible and what can we do? And unless you are really measuring emissions, it's very hard to address this question. The third dimension, and that you probably are seeing that everywhere, everyone is talking about sensors. Most sensors are bad, really, really bad. Maybe a few are reasonable, but they're not commercially available. The first one is the Copenhagen wheel. In Copenhagen now they have actually NO2 sensors on their rental bikes. How well do they compare with, these are sensors that cost 200 to 500 euros. The condensation particle counter that we're using costs about $10,000, $12,000. So So there is, I mean, you are trading, you have trade-offs, but looking at the power and the potential of this human-centric air pollution sensing, and actually evaluate the potential of an embedded network of monitors in the generation of urban air quality maps in real time, because you're getting the data in real time, so you can actually test different ways to interpolate and generate real-time air quality maps. Even though I do put that as my ultimate aim, that I don't think I would want to engage in right now because I'm not in sensor development and the technology has not matured. This is actually an NIH proposal on which I am participating with a PI in the States, and if it does get funded, we will have access to sensors that were developed at Imperial College by a guy called Rod Jones to install them and compare the measures that you get from an embedded network with personal exposure measurements and with fixed site monitors and with modeling, because that's really my prime interest. This leads me to the acknowledgements. I'd like to acknowledge, obviously, collaborators, Scott Weikenthal, Naveen Lower, Mark Goldberg from McGill and Health Canada, with whom I've done a lot of this work, funding agencies, and then obviously very, very helpful students who actually did the work. This I end my presentation. Thanks. Pardon? Yep. Yeah. 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 Because otherwise, yeah, I mean, that's the thing. If you get OD pass and then you're assigning these cars and then you compare that with the original output from Vizoom, it could be you could be terribly far off from what you are getting. Yeah. Yeah. No, all of the paths. All, yeah, yeah, yeah. It's huge, and this is run in stochastic user equilibrium. So I mean, the path array has millions and millions. Yeah, and that's why we go ahead. So basically, that's the thing. It is probabilistic. So basically, you are looking at the paths that have the highest volumes, and you are assuming that these are the most desirable, but then other people are going to be on other paths. And so eventually there's a lot of randomness that goes into this. Now what we have done, because we were so concerned, this was the one thing that we always rerun 30 or 50 times. And then whenever we're giving a result, you are calculating, you are generating this error bar to see where you are. It didn't seem, with respect to others, right? With respect, you never know. It's emissions, you don't know where the truth is. But with respect to the uncertainty in other inputs, the path allocation process didn't seem to generate a very wide variability in the results. So whether or not you were, making mistakes, same thing with the vehicle allocation. As long as you have the amount of vehicle, the number and the characteristics of the vehicles in that FSA, if you're giving different people the wrong type of car, but you're respecting the constraints of how many cars they have and the general types of cars that they have, because we have that, then it didn't seem to also generate a very high variability in the outcomes. This is in Vizoom. Vizoom, yeah. Yeah, yeah, yeah. Yeah, it has to run, it's within 60 iterations, so much more than what you would do with Emmy. With Emmy, I'm suspecting within 20 or 30 iterations, the model converges. So it was about 50 or 60 iterations.
Thank you for a wonderful overview of the health complexity between trying to figure out how vehicles are impacting health and all the steps to whether we need to better model traffic, better model emissions, better model dispersion and concentration, better model what people are, get exposure or high exposure to health outcomes.
Yeah.
There's many steps to kind of hinted at the end that you see the way forward is in terms of better understanding emissions. You talk about real-life emission factors and looking at how different driving patterns, acceleration, for example.
Yeah.
So do you see that as the biggest unknown in that whole continuum? Is that why you want to focus there, or are there other unknowns?
I mean, there's obviously other unknowns. I think that when it comes to the effect of the microenvironment, the meteorology, there has been really tremendous research in developing CFD models that are doing very well at capturing the near road environments. I think the biggest uncertainty is that what is the amount of emissions that we're getting? If you're not interested in emissions, you're actually measuring near road air quality. You could get by. But at the same time, again, I always say, right, I mean, there's the soup of pollutants. We're tracking maybe one or two. We're saying NO2 is a very good marker, which apparently it is. A lot of studies are showing very strong correlations, and a lot of people are saying, well, you know what, just stick with NO2. It seems to be actually a robust marker of traffic. But I mean, this is all to say that I do think that the actual emissions are right now the weakest links. Models like MOVES they just take base emission rates. They're not instrumenting a lot of vehicles. The model MOVES is based on emission factors from Mobile 6, which actually was based on hundreds, not even thousands, of instrumented vehicles on the one or two California roads under, the federal legislation at the time. So we really don't know how well these models and how well these emission factors are. And again, I mean, models like MOVES don't have the range of pollutants. I mean, they have more of the criteria, air pollutants. It might be easier to measure them, but you don't have the whole gamut as well. But with PEMS, you can measure a lot more. Yeah. Oh yeah, they are. Yeah. 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 Yeah, I mean, I mean, Mark Goldberg is my collaborator. He's an epidemiologist, right? And he always says, standards mean nothing. They mean nothing. They are useless because we are detecting, these are epi studies, very large population studies, where they are detecting associations at levels that are way lower than the standards, at levels sometimes that, we're even struggling with, the detection limits of our instrument. I mean, sometimes you have levels below the detection limit, but you're not even sure whether these are safe levels or not. Maybe this is because we are able to explore better associations, we are able to detect better effects, or because the doses are different, because more people are exposed, because people are closer to the sources of traffic. But yeah, I mean, this is just to say that, the standards really mean nothing. And the standards are only established for those pollutants with quote-unquote known health effects. Black carbon, ultrafine particles, there are no standards for them. We don't even know yet what's the safe level.